So first of all, hello to everyone and welcome to our fourth Continuum Town Hall. For those of you who I've not yet met, I'm Liz Walls. I'm the lead developer of the Continuum Wind Energy software, and I'm joined by Erin Reckley, the product manager of Continuum. We're really happy to see all of you here today as we continue our six-part lecture centered on the Continuum wind flow model. And we actually have quite a bit to cover today, so let's just jump in and take a look at the agenda and see what we have. Oh, I gotta take control. We'll take a look at the agenda and talk about what we'll be covering today. So we'll kick off the town hall discussion going over an explanation of the status of the new release, 1.3.2. For those of you who joined us in the previous town hall, you may recall that we were talking about this release last time, and we were hoping to have it released sooner, but we had some requests for some additional features and improvements. So we'll explain all that about where we are with that release and what to expect with the new features. And then after that, we will jump into the heart of the presentation today, and that is part 2 of 6 of the lecture series entitled Continuum Wind Flow Model Explained. And so in this session, we will expand upon some of the concepts that we talked about last time, mainly train exposure, and how that translates into flow types and how the base equation for the continuum wind flow model was derived. After that is done, we'll open it up to any questions that you may have, maybe questions from last time, questions on the software, the new release, anything is on the table. So that will be a chance for you to pose those questions. And then we'll finish off the session with a reminder and overview of the Continuum Contributor Program, which explains how to get involved in Continuum, how to contribute, whether it's through coding or research and those types of things. So that's what we have scheduled today. But before we go any further, I wanted to take a quick minute to highlight this community, this global community that we're seeing grow here, which I think is pretty cool. So I just took a minute to look at the list of folks on the RSVP list to see where we're all from. And there are people from 10 different countries who are on this call today. So I just think that's really great that the software is being used around the world and people are and joining us in this community to further the software and to further wind research as a whole. So I just wanted to give a shout out to all these countries and excited to see the number of these countries grow as we continue to hold these town halls. And if I did miss a country, please let me know, but I think I got them all. So welcome to you all. Really happy to have you all here. Okay, so now down to business. So the next release, version 1.3.2. As I mentioned, yes, we did talk about this last time, and this list of new features and updates, a lot of them we've talked about already. So I'm just going to focus on these top 3, which are the new features that were requested over the last few months, and I'm excited to share with you. I also was really hoping that it was going to say available now during this town hall, but there is just, I'm troubleshooting map generation using parallel threading, and I'm very close, but not quite there. So I'm really hoping that it will be the next couple of days, but when the new release is officially ready, we will send out an email to everyone on this town hall, as well as post it on the website. So now let's talk about some of these new release updates for the software. So the first one was brought up by a user here in the US who is using the US National Land Cover Database in his modeling. For those of you who don't know what a land cover key is, the land cover key simply converts land cover codes into a surface roughness and a displacement height, which are then used in the wind flow model. So land cover codes can be things like row crops or grass and pasture, and they have different levels of surface roughness. Well, in the US, the National Land Cover Database, when you download those files, now there might be an area where there's missing data. And a missing data land cover code for the US NLD-CD is 250. And so there wasn't a way earlier for Continuum to recognize and ignore missing land cover codes. So now that's available. So for the US National Land Cover Database, 250 is the built-in missing land cover key, but you can add that for any land cover data that you're working with. And again, it just tells Continuum, ignore this, it's missing data, don't include these values in the calculations. The next new thing is related to the site suitability tab, more specifically when conducting shadow flicker modeling. we now have a maximum shadow distance setting. So if you you can change the value in this text box here. It's set at 2,000 meters or 2 kilometers by default. And what that is doing is it is limiting the distance at which a turbine still inflicts a shadow on a zone. So once the turbine is more than 2 kilometers away, or whatever setting you put it to, that shadow is no longer impacting that zone. So that's something new. And the last one, and the one I'm most excited about, is the new updated time series tab. And so this was requested by some users who are using the time series module, but the previous version, or I should say the current version, is limited in that it only lets you look at data on a turbine by turbine basis. And it was requested, well, hey, I want to look at the wind farm as a whole. What is the wind speed and gross production of the whole wind farm, not just turbine by turbine? So I started taking a look at it and realized, wow, this tab, it needs an update. It needs a bit of a makeover. So let's go over what it looks like now. So now when you go to the time series tab, there is a top panel and a bottom panel. We have the tabulated data in the table above and then a plot on the bottom. And you can move the windows up and down to take a closer look at either the table or the plot. And there are different options of ways to look at the data. So there is a drop-down menu at the top here named Analysis. And by default, if you go to this tab, it'll be selected as Time Series Hourly. So you can take a look at all the hourly estimates, average wind speed, gross and net production, as well as wake loss, again, on an hourly basis. But you can switch that drop-down to monthly. So that condenses the data down now to monthly. Might be a little bit easier to look at or compare. And so you have that option available to look at the same data, but again, condensed down into monthly. You can take it a step further and condense it down and take a look at the time series on a yearly basis. So those are the three options, hourly, monthly, yearly, that you can view and analyze the time series estimates. Furthermore, you can now zoom in to these time series data. So you just hover over the data, the plot, and use your mouse wheel to zoom in and out. And when you do that, the table will scroll to that same time period that you're looking at. So you can zoom in and really hone in on an area that you might be interested in for whatever reason. And the data table, or the data will scroll to the same value so you can take a look at the data in a closer way. And then you can also use these arrows in the top, these left-right arrows, to march forward or backward through the data, again, to take a closer look at what the simulated estimated time series values are. And then the last option on this new time series tab is that we can now look at monthly trends. So the last drop-down option from the drop-down menu is Trends Monthly. And so it changes the table. So now each column is by month and each row is by turbine or the whole wind farm. And it shows the long-term values as well as year by year. And so this is really handy because you can turn the years on and off. So you can really focus in and have the dashed line is the long-term average on a monthly basis for wind speed. And this is just one particular year you have selected. So you can see that there was a month in the fall where the winds were, much above normal. So that could explain, increased production. So we're excited about this new time series tab. Really looking forward to feedback, suggestions, all that sort of stuff when this gets released. So don't be shy if you have comments or ideas to make it better. Really looking forward to hearing you on that. Okay.
Absolutely. So going to switch directions a little bit and get into the bulk of today, our lecture series, session 2. So just kind of little overview again of kind of this whole series that we've been putting together. We've got our big continuum equation, and we're taking bite-sized pieces as we're kind of stepping along throughout this lecture series. So last session, we talked primarily just about terrain exposure and how we were calculating it and what it meant. And today we're going to be talking about flow types and kind of bringing that terrain exposure back into it as well. Next session, so in 2 months, we'll be talking about surface roughness as well as displacement heights and those components of our equation. And then session 4, the new elevation and valley components, models that you can currently toggle on and off within the model itself, and how those get calculated and why, and all the background of that. And then session 5 and 6, we're talking about our model coefficients and how they're calculated, what each different model coefficient is, how it's applied to each of the individual components. So just a little bit of recap from last session where we were talking about terrain exposure. Just kind of what is terrain exposure? Again, that definition, it's the average elevation difference between a site of interest, so like a turbine, and the surrounding terrain within any specified radius. And then it's going to be weighted by our inverse distance. So when we're looking at terrain exposure, specifically with the continuum model, remember, we're looking at it in sector-wise portions. So we're looking either at the northern sector or we're looking at the southern sector. So we're taking little pie wedges and seeing, okay, what is the average elevation difference between my site of interest at the middle of my pie related to that specific wedge and that elevation within that wedge, like that. And so how do we actually calculate this? Again, here's that equation. We're taking all of the different elevation data points within an upwind and a downwind sector within our little wedges. And we're saying, this is my site of interest. How do all of these little individual data points of elevation compare to our site of interest? And we're just kind of stepping through and going through all of the different data points that are in our wedges for both the upwind and downwind within a specified radius. That's it. Yeah.
Okay, so we've been talking a lot about terrain exposure, but you might be wondering, well, how does this tie into the wind flow model? Why does the exposure matter? Well, it turns out that there exists this linear relationship in nature between wind speed and exposure. And it was Jack Klein, who I believe is on the call. He should be. Jack was the first one to observe that this relationship exists in nature. Again, this linear relationship between exposure and wind speed. And this goes back to, let's see here, 2007 was the first time that Jack introduced this concept of exposure-based modeling to the wind industry and demonstrated this linear relationship that exists in nature. And when I learned about this modeling technique from Jack, I was immediately intrigued, but I couldn't help but ask, okay, this is cool, but why is there this relationship between wind speed and exposure? Is there a way that we can understand this from first principles? Can we maybe derive it? So that's what we're going to talk about here, is how this linear relationship can be derived from first principles from the Navier-Stokes conservation of momentum theory. So hopefully you guys have hopefully you had some coffee today, this morning, and ready for some partial derivatives. And don't be scared, it actually is not that complicated when it comes down to it. So a quick recap, or perhaps an introduction for some, what is the conservation of momentum theory? Essentially what it says is that the change of momentum of a moving fluid is equal to the sum of the forces acting on it, and that the acceleration of the fluid is directly proportional to the net force acting on the fluid and inversely proportional to mass. So the equation that everyone should be familiar with from high school physics is force equals mass times acceleration. So that's the most basic form of the Navier-Stokes conservation momentum. For our purposes, though, we're going to expand it out into its more full form, where we have acceleration on the left-hand side. So it's a change in velocity with time, and change in velocity within all the different x, y, z directions, and that is equal to the sum of the forces. And the forces can be categorized into three groups, and those groups are pressure, so pressure acting in different directions on that fluid, and then shear, so pulling against the movement of that fluid, and then lastly gravity. So those are the forces generally, in general terms, that apply to a moving fluid.
So with that kind of background of knowing the Navier-Stokes, kind of the F equals ma, just broken up into more terms, we are going to start looking specifically at the downhill flow and kind of all the things that are going into it. So we're going to use a control volume approach. And so we're basically going to say, I have a blob of air, parcel of air, and it's at a higher elevation. It's going to start moving downhill. So we're going to take that blob of air and say, okay, well, what are all of the forces that are acting on it? And then can we use that equation that Liz was just mentioning and see what is the acceleration going to be? So we've got a little cartoon graphic to kind of show this. So we've got our little blob of air, and it's going to be moving downhill. And we've got four different forces that we're looking at initially. Well, I guess we're looking at in general. So we have two different pressure gradient forces we have pressure gradient in the vertical, and then we also have pressure gradient in the horizontal. So those are what these two, are you guys seeing my mouse? Sorry. Okay, perfect. So these are the two pressure gradient forces that we're looking at. But then we also have gravity that's trying to pull our parcel down as well. And then in the opposite direction of our flow, we have a shear force that's trying to pull it back uphill. So the acceleration of this little blob of air as it's going downhill is going to be equal to all of these forces that are acting on this blob. So we've got our equation again, the F equals ma, just kind of expand it out a little bit. And now we're going to say, okay, how do these forces actually now fit into that equation? So we have now four terms because we have four forces that are acting on our parcel. So we have the first two terms, those are our pressure gradient terms relative to theta. Theta is just kind of the slope of our elevation. So if you've got a steeper slope, you're going to have a bigger theta, kind of more gradual slope, it's going to be a smaller theta. So those first two terms, they're relative to our pressure gradient forces. That third term, that's our shear force, again, kind of in the opposite direction of our flow. And that last term is gravity. So I do want to point out real quick, though, the signs of all of these. So you can see the first term, the pressure gradient force in the horizontal, is positive. So this force is going to be trying to pull our blob of air down the hill. It's helping accelerate. And then this last term, gravity, you can see it's pulling it down. It's pulling it downhill as well. So that is also positive. On the other side of the coin, we have our vertical pressure gradient force and our shear forces. And those are trying to pull our little blob of air back uphill. So those are going to be negative components within the downhill flow. So we're going to take it a little baby step further, and we're going to start comparing the acceleration at two different sites. So we're going to say our sites are close to each other, so they're pretty similar conditions. And the only difference that we really have is that one of our sites, site 2, has a larger terrain exposure, so a steeper slope. There's more terrain variability. I guess not variability. The average elevation difference is greater than what we see at site 1. So the acceleration and wind speed at the two sites is going to be due to downhill flow. So all our little parcel is right behind our turbine and it's flowing downhill. So we can bring that equation that we just talked about, all the forces acting on things, and have two different equations, one for site 1 and one for site 2. And so we just have little subscripts 1 or 2, depending on what site we're looking at. Now we can start taking in the conservation of momentum theory between the two sites and set them equal to each other. So you have the site 2 acceleration minus site 1 acceleration is equal to 0. So kind of just start plopping those bigger equations kind of up a little bit on the slide into that concept. And we just start moving things around so that they're right next to each other. And we are going to assume some things. Like I said, they're very similar sites, similar site conditions. So the density is going to be the same. The horizontal and vertical pressure gradient forces are going to be the same. And then the surface roughness is also going to be the same between the two sites. So when you start applying those assumptions, we can start to combine things get removed and drop out. We end up with this equation here. So the acceleration at site 2 minus the acceleration of site 1 is the pressure gradient force in the horizontal over rho times the change of the cosine theta minus the pressure gradient force in the vertical over rho times the change in the sine of theta plus gravity delta sine theta. But the change of cosine of theta is going to be way, way smaller than the change of sine of theta. So we're just going to basically say it's not really going to be important in this equation. So it's going to drop out and we get a new final equation. So the change of the acceleration is just related to gravity minus the vertical pressure gradient over rho multiplied by the delta sine of theta. and that is our downhill flow change of acceleration. So we're going to take that. And I always said we took a baby step. We're going to take one more baby step and now start applying it and figuring out wind speed differences. So going to multivariate calculus, we know that acceleration is the derivative of velocity. So we're going to take the material derivative of velocity and just expand it out and expand out those acceleration values into its full dv dt's. And so we can have more variables to play with, really. So we've got our A2 minus A1 broken down into our material derivative. But we're also going to bring back that same equation that we just had. The A2 minus A1 is related to the to gravity and the vertical pressure gradient and delta sine theta. So basically, we're just going to set them equal to each other. We've got the big portion, the big material derivative on the left-hand side of A2 minus A1, just all broken up into its components. And then on the right-hand side, it's the sum of those forces. And so when we have that, we can start making a few more assumptions and building out our full downhill flow definition. So the assumptions we're going to make, we're going to make the assumption that it's steady state conditions. So anything that is dt is going to get set to 0. So we cancel those out. We're going to assume 2D flow. So anything dy is going to also get zeroed out. And that these two components are equal at sites. This is kind of the same assumptions that we're making previously. We're just continuing those assumptions. So when we cancel those things out and making those assumptions, we end up, and we rearrange everything. There's a lot of rearranging going on in these equations. We end up with V2 is equal to V1 plus all of that that you can see on the screen. We're also going to tell you, hey, sine of theta, that slope of the flow basically is related. It's directly related to exposure over radius. So we're going to swap out that delta sine theta with the change of exposure divided by the radius. So that we're starting to tie in exposure, kind of that building block of the continuum model, into our downhill flow equation. So this denominator of this, this kind of little chunk within our equation, that is going to be encompassed within one of our coefficients. And the dvx over dx and dvz over dz, those are related to the terrain complexity. So we know that the downhill flow, the acceleration, is related to terrain complexity. And then if we look at the numerator side of it, we have the pressure gradient force in the z component over rho. Well, if any of you are atmospheric scientists, anytime you're hearing pressure gradient in the vertical, you should automatically be thinking atmospheric stability. Like how is my blob of air going up in the atmosphere? How stable is this air? So we know that this is related to atmospheric stability because we do still have that vertical pressure gradient force within our coefficient as value. So we kind of take all of those things that aren't in the change of exposure, and we're just going to package it all into one coefficient for our downhill flow. So everything just gets jammed into one value or one variable, and that variable is calculated. It's going to be site specific, and it's one of the cool things about Continuum is how it's calculated. We'll get there. We're not going to talk about it right now, but in one of the later sessions, we'll talk how are we actually calculating out what this coefficient is. So it makes it pretty elegant, really, kind of the change of wind speed when you are looking specifically at downhill flow. It's just V2 is equal to V1 plus M multiplied by the change of terrain exposure between your two sites.
Okay, so That was a great explanation of what's happening when wind is flowing downhill. So now let's take a look at the opposite situation where wind is flowing uphill. So what we're looking at here is a similar free body diagram, except now we have wind going uphill. And Aaron was making a point of thinking about directions of these forces in relation to the direction of the flow. So let's take a closer look. So it's the same forces acting on this blob of air as we had in the downhill flow. So we have pressure gradient forces in both the horizontal and vertical directions, as well as shear force and the force of gravity. Here's the equation for Navier-Stokes, and then looking at the sum of the forces on this blob of air. So now let's take a look at the signs of these different forces. So with the horizontal pressure gradient force, that's always going to act with the flow of the wind. So that is helping, that is moving it along. And now we actually have the vertical pressure gradient force. That's also giving us a boost. So that is also helping to move the air up the hill due to that vertical gradient. Shear, always opposing the force of flow. So that still has a negative sign. And now the wind, as it flows uphill, now we have a negative sign for the gravity force because we have gravity that's acting against the flow of the wind. So similar situation as downhill, but some signs are flipped again due to the vertical pressure gradient force and gravity working with and against the flow of the wind. So yeah, so a pressure gradient force is acting with, and then gravity acting against the flow. So let's take a similar look like we did for downhill flow. It's going to be a simple example where we have two sites that are really quite similar in terms of conditions. The only thing that's different is the upwind exposure. So in this example, we have site 2 that has a greater upwind exposure than at site 1. So it's a steeper terrain upwind of the site than at site 1. So if we take a look at the acceleration at both of these sites due to the uphill flow, it's a very similar approach to what we looked at for the downhill flow. So we have the some of the forces acting on site 1 and site 2. Pressure gradient forces acting with the flow, shear and gravity acting against it. We're going to apply the conservation of momentum. So we're going to subtract the two equations, acceleration at site 2 minus 1. We're going to expand that equation out. So we're just popping in all those terms for site 2 acceleration into that equation. And rearranging some terms and breaking out the change in acceleration. And what we end up with are these three terms. But again, we're going to make the assumption that the delta cos theta is going to be much, much smaller. So that term goes away. And we end up with the change of acceleration at the two sites is equal to this vertical pressure gradient force minus gravity times the change in the sine theta. We're going to use that same material derivative. So we're going to expand out the acceleration term, keeping in mind that we have the sum of the forces that we just found on the previous slide when it comes to uphill flow. We're going to plug those or set those equations together. So the expanded version of acceleration using the material derivative equal to the sum of the forces. We're going to make those same simplifying assumptions, steady state conditions, 2D flow, and that the wind speed variability or wind speed distribution are the same at site 1 and site 2. They're similar sites, just different slope and terrain. That's really all that's different. And so when you do that, the equation simplifies to the wind speed at site 2 is equal to the wind speed at site 1 plus this term on top that has to do with the vertical pressure gradient force. And as Aaron mentioned, it's related to atmospheric stability. And then on the bottom is the wind speed variability in the X and Z directions, and that is related to terrain complexity. And so we can swap out the sine theta for exposure. And really, yeah, we could use sine theta, but what we found and what Jack has found with his experience as well is that just looking at the slope of the terrain doesn't do a very good job at capturing the variability. Exposure is a better measure of the terrain slope instead of just a simple slope calculation. So we swap out sine theta for exposure over radius, and then the terms can be summed together or condensed into this one linear coefficient. So what we just did here is that we showed this, yes, it makes sense that there's this linear relationship between exposure and wind speed in nature. Now we understand why. It has to do with conservation of momentum when you have sites that are similar. It's just changing the terrain. It's just the change in the terrain, upwind and downwind, and how that's affecting the momentum. All right, I'm going to take it a step further. So uphill is interesting. Uphill is not quite as simple as downhill flow. And the reason for that has to do with a phenomenon that we call induced speed up. Because what happens when wind is traveling over a hill, there's a pressure buildup that happens just upwind of that hill. And what that does is it causes an induced vertical pressure gradient force and induces an acceleration over that hill. But at the same time, as we mentioned, as we're traveling uphill, we're fighting against gravity. We're fighting against the shear forces as well. And those pressure gradient forces are acting against the shear. So it's like a push and pull between these different forces acting on the air as it travels uphill. And so in the continuum model, what we say is that the point at which the pressure gradient forces are equal and opposite to the shear and gravity, so the forces that are pushing the wind and the forces that are pulling the wind back, the point at which those are exactly the same but equal and opposite, that is when we have the critical upwind exposure. And what that means is that if the upwind exposure at your site is larger than the critical upwind exposure, then that means that, let's see here. Yes. Oh, I think we might have these backwards. We have gravity winds. Sorry, my bad. When we have wind traveling uphill and the upwind exposure is larger than the critical upwind exposure, then that means the force of gravity wins. The force of gravity is larger than that vertical pressure gradient force, and the wind slows down because gravity is pulling it back. But if the upwind exposure is less than that critical upwind exposure, if it's less than that value, then that means that the vertical pressure gradient force is larger than gravity. It's overcoming the force of gravity, and that's when you see the speed up. So in uphill flow, we have that term again, critical upwind exposure, that defines the transition point between when you have your induced speed up to where you have uphill flow where the wind actually slows down as it travels up fighting against gravity. A typical value for the critical upwind exposure is about 20 meters or so. As Erin mentioned briefly earlier, in the continuum model, all these coefficients, including the critical upwind exposure, are found using a site calibration / machine learning technique, which we'll explain in depth in a future session. But just know that in general, 20 meters-ish is typical for critical upwind exposure. Okay, now tying it all together. So combining the upwind and downwind sectors. So in the continuum model, we're saying that the momentum of the wind can be affected by what's happening upwind as well as what's happening downwind. And so what we do is we sum the total effect of the upwind and downwind terrain changes to come up with an overall effect on the wind speed. So it's quite simple. So again, this is the downwind equation. So we have the wind speed at site 2 is equal to site 1 plus the coefficient times the change in exposure. But in the downwind direction, so we talked about the downhill example, but you can also have an uphill flow in the downwind direction. So where the train is sloping up downwind of the sector. And so these would be the two equations that are used to estimate the change in wind speed due to changes in downhill flow in the downwind direction. And this is the equation for the change in wind speed due to the changes in the downwind direction when there's uphill flow. And you'll notice the subscripts here are different. So we have DH and UH. So we have different exponents that determine the sensitivity of the wind speed to changes in the exposure for downhill flow versus uphill flow, because they are not always, but sometimes they're different. And then on the other side, in the upwind direction, there can be three types of flow that we talked about. So there can be downhill flow where the wind is flowing down towards the site. Then we have induced speed up that we just talked about, where the upwind exposure is less than the critical upwind exposure, so you get induced speed up. And lastly, uphill flow, where the wind decelerates as it's traveling uphill as the gravity is winning the fight. And then notice the subscripts down here. We have DH for downhill, SU for speed up, and UH for uphill. So there are three different flow types that are defined in the continuum model. That is downhill flow, uphill flow, and speed up. And there are coefficients defined for each of those different flow types. And then when it all kind of comes together, It's the total wind change between two sites is equal to this coefficient upwind, depending on what flow it is, will determine what that coefficient is, multiplied by the change in exposure, plus your downwind coefficient, again, depending on the type of flow happening in the downwind direction, multiplied by the change in exposure. And absolutely, these slides will be available on the website as we have with previous town halls. So yeah, absolutely, we will definitely make these available. Okay.
So now we did all the derivations. That's the hard part. So now we kind of start, we're going to put them into practice. And we're going to take those three sites that we looked at last time and kind of continue forward with them. We had Kingfisher Wind, Western Spirit, and Allegheny Ridge. So Western Spirit's over in New Mexico. It's moderate terrain complexity. Kingfisher Wind is in Oklahoma, very flat there. And Allegheny Ridge over in Pennsylvania, it's a ridgeline project, so very highly complex terrain. So just for all your reference again, these are where all the turbines are located, those red dots, and then the topography maps around it. So you can see with Allegheny Ridge, very, the terrain varies a whole lot. We're on a ridge line. And then looking kind of on the other end of the spectrum with Kingfisher, it's very flat, not a whole lot in terms of terrain going on with those. So first we're going to look at Allegheny Ridge. This is the high complexity ridgeline project. So we're going to look at two different turbines. So we're taking two sites and we're going to see, okay, what's the wind speed difference between the two? So we're going to be looking in the 270-degree sector. So the 270-degree sector is going to be our upwind sector, and everything in those little wedges, those elevation data points are what we're going to use when we're calculating out our terrain exposure. And then our downwind sector is the opposite of that. It's the 90-degree sector. So everything in the right hand or the eastern side wedges, those are going to be used within our exposure calculations. So these same figures that we were showing before, kind of seeing where are all the data points of the elevation that we have for each of these turbines. So for T16, the upwind is on the left-hand side of that graph, downwind is on the right-hand side. So you can kind of see where the site that we're specifically looking at is relative to the rest of all the elevation data around it in those sectors. And then the same thing with T12. You can kind of see the T12 is right. It's a higher elevation than kind of the surrounding elevation around in those specific sectors. So just kind of put them onto one plot. So we've got upwind and downwind. T12 is in the blue. T16 is in the green. And we want to first, let's look at the terrain exposure itself. So what can we say about the signs of the upwind and downwind terrain exposure for each site? So let's first look at T12, so all the blue dots. So at distance 0, that's where our site is. Everything on the left-hand side is lower than our site of interest. So because everything else, our site of interest is higher than everything else, we have a positive exposure in the upwind direction. And then kind of looking in the downwind sector, all those blue dots, our site of interest is also higher than the rest of our wedge. You can kind of see it's higher up than all the rest of the dots. So in the downwind sector, our exposure is also positive because again, our reference point is our site of interest of where we're seeing what sign our exposure is. So looking at T16, it's kind of in the same elevation as T12, and we're looking at the green dots now. So most of the green dots on the upwind side are lower. Pretty much all of the dots, all of our elevation data points are lower than our site of interest. So we have a positive upwind exposure. And then the same thing on the downwind side. The site of interest is higher than the rest of the data. So we have positive for both upwind and downwind for both of our sites that we're looking at. Both sites or the sites are higher than everything else around it in these two sectors that we're specifically looking at. So in the upwind sectors, we're going to have uphill flow. So we're going up the hill to our site that's at the very top of that ridge line. And then in the downwind sector, we're at the top and we're going to be having downhill flow. So our little blob of air is going to be traveling downhill in that specific sector. So here are the values that we need to know for each of these upwind and downwind sectors for these two sites. And we're going to carry that over to this next slide. And I'm just going to tell you these coefficients. We know our equation, and here are the coefficients that we're going to be working with. So we want to know what is that wind speed difference that's going to be between T16 and T12 within that 270-degree sector. So we bring back our fun little elegant equation, and we just start plugging numbers in. We have everything that we need, and we can see what the change of wind speed is. So we're just expanding things out, and we start plugging in those numbers, and we end up with a change of wind speed of 0.64 meters per second. So what that means is that the wind speed at T16 is going to be 0.64 meter per second higher than the wind speed at T12. We don't necessarily know what the wind speed is at T12. All we're trying to figure out right now is what is the difference between these two sites that we're looking at? How can we relate them to each other? And just what the delta is. We don't know the actual value. We just know T16 is going to be higher than T12 by this 0.64 meter per second.
Okay, let's take a look at another example with terrain that's not as complex. This is a site in New Mexico called Western Spirit. This is a map of the topography, and it's a little tricky to see, but what's happening here is the terrain is sloping down from the west down into the easterly direction. The plot up here is showing the windrows, and so we'll be taking a look at a slice of the terrain in the 300-degree sector in the upwind direction and 120 in the downwind. So we have our first example site is T3 up in the north here, and the green wedges are highlighting the upwind and downwind sectors, similar to the example that Aaron just showed. And then we have a plot of the terrain in both the upwind and downwind direction. So here it's clear, right? The terrain is sloping down in this direction, which makes it very favorable for a wind farm, since that's the prevailing wind direction and also direction of the terrain slope. So that's why a ton of wind farms are getting built in this area. So that's T3. It's a nice steep downwind exposure. So you'd expect, the wind just to come flying down this slope. Meanwhile, down south, we have similar terrain-ish. We still have terrain that's sloping down from the west to the east, but it looks like maybe it's not as steep as at T3, right? It looks like it's not quite as extreme, especially in the downwind direction. So these are our two sites of interest. And let's take a closer look at what the calculated exposures are at the two different sites. So here they are laid on top of one another, the upwind and downwind exposure at the two sites, T16 and T3. And what can we say? Okay, so T16, we have a negative upwind exposure. So recall that negative upwind exposure means that your site is lower than the terrain in the upwind direction. So that means that the wind is flowing down towards your site. The wind is going downhill with a negative upwind exposure. On the other side of the site is the exposure is also positive because the wind, again, is flowing down. The site is higher than the terrain in the downwind direction. That equals a positive downwind exposure. T3, same thing, negative upwind, positive downwind. We have downhill flow in both, at both sites. We have in both directions. We have downhill flow in the upwind direction, downhill flow in the downwind direction. Pretty simple. The wind is just flowing down this slope, right? And taking a look at the values, we can see, okay, yeah, T3 is steeper in the downwind direction. So check that out. The exposure is 43 meters-ish compared to a downwind exposure of 25. So immediately like, T3 should have a higher wind speed because that downwind exposure is higher. That's encouraging wind to go, ripping down that slope. So those are the values. And then also the upwind exposure at T3 is more negative. So that means that it is steeper, that the terrain is higher in the upwind direction, which is also very conducive for a good wind flow. So we know those are the values for exposure. Now let's see how the estimated wind speed works out. Again, in a different session, we'll talk about the coefficients. We'll talk about the default coefficients that are available in Continuum, because you can model with just one Met tower, and that's when the default coefficients are used. But really, one of the main strengths, or one of the big strengths of Continuum, is that the model coefficients are determined on a site-by-site basis based on the Met tower data. So again, we'll get into all this, but just know that the coefficients are site calibrated, are specific to a site based on your Met data. And if you don't have them, then the default coefficients are used. Okay, so we have downhill flow for both upwind and downwind. So that's why the coefficients are the same in value, but we have a negative value for the upwind just due to the sign of the negative exposure, but they're the same magnitude. Okay, so now we're just going to pop those equations into our continuum model, the base model. And so we have the two coefficients for the upwind and downwind flow, and then the change in the exposure in the upwind direction, change in exposure in the downwind direction. And this is saying that, yes, in fact, according to the model, the wind speed at T3 should be higher than the wind speed at T16 by about 0.34 due to both changes in the upwind and downwind direction. So that's what's really important to remember. It's looking at both what's happening upwind and downwind and how those changes in exposure will impact the momentum at your site. Okay, last example. Last example is the induced speed up. Okay, this is a site in Oklahoma called Kingfisher Wind, and we'll be looking at a slice of wind through this direction sector, upwind of 330, downwind of 150. And so you can see that, yeah, it looks like uphill flow, but it's not very steep, right, on the upwind side. And then on the downwind side, for sure, there's downhill flow there at T24. And then our next example site is down to the southwest, and that is T28. The terrain is also sloping up in the upwind direction, but not by a large degree. It's not a huge change in elevation. And then there is a positive downwind exposure, but it's not huge. It's relatively small, especially compared to Allegheny Ridge. This is much simpler terrain. Okay, so what can we say about these? Well, we have positive exposure in both directions. So at site T24, the elevation is higher in both the upwind and downwind directions. And same thing at T28, we have positive exposure in both the upwind and downwind direction. But what is happening here is that the upwind exposure at both sites are quite small, 9 meters at T24 and 16 meters at T28. And recall that we said that typically the critical upwind exposure, and again, that's the point at which the forces due to gravity is equal and opposite to the forces due to the pressure gradient forces. The point at which they're equal is around 20 meters for the upwind exposure. So we have upwind exposures at these two sites that are less than that critical upwind. So we're saying that this is going to be, there's going to be some induced speed up happening at these two sites. Okay, so now let's see how those numbers come out. Here we have the coefficients. Again, we'll get into all that, how those are defined in a later session. And we're just going to calculate out what the estimated difference between the two sites would be based on the flow type and the exposure. So upwind, we have the induced speed up. So notice that this is a positive sign, not negative anymore, like we did for the uphill flow. And then we have the downwind exposure or downwind coefficient multiplied by the change in the downwind exposure, which is really very similar, right? The downwind exposure is not very different between the two sites. And so what we see is that there's a modest change in wind speed, mainly due to the induced speed up of around 0.04 meter per second, and a slight increase due to the small change in the downwind exposure for that, the downwind flow. So those are so yes, the wind speed at T28 will be 0.05 meters higher than the wind speed at T24. And as Erin mentioned, right now we're just looking at delta wind speeds. You might be asking, well, how does this tie into the wind flow model? Well, that's where Met towers come in. So once we introduce a Met tower into the equation, then the wind speed at the Met site will be that site 1. And then you'll be measuring or estimating your wind speed at site 2 based on the wind speed measured at your Met site and the differences in the terrain exposure at your Met site to any site of interest, whether it's a turbine location or a map node. Whew, okay, that is it. That is the derivation of the continuum base model. There is more to it, as we said. That was a lot of theory to cover. So if you have questions, you can email us later, but And we do have a little bit more to cover when it comes to the Continuum contributor program, but I will open it up quickly if there are any questions off the bat, or if not, again, feel free to email and send in your questions. Syrian, okay, T12, you have a point at the same height at approximately. Right, so because in the exposure, so Syrian is asking for one of the example sites, same height. So I think, Syrian, you're asking how does the terrain, say 2,000 meters out, impact the exposure calculation? So recall that in the exposure calculation, all of the elevation values are weighted by the inverse distance. And so that places a much higher weighting on the terrain that is within a kilometer-ish. And so the weighting really starts to diminish as you get further out. And so it's hard to say in this particular example exactly how that terrain at 2,000 meters impacts things, but just know that it's really the terrain closer by that really impacts the exposure. But things can get complicated when there is, a lot of variability and it doesn't follow your typical terrain slope. Okay, and then, Waleed, I wish you luck in applying to work at wind farms, and there's a need for wind farm operators for sure. And then to email for questions, you can go to the website and email through the Continuum contact page. And then we'll also share our contact email at the end of this presentation. Okay, we only have a few minutes left. So let me turn it over to Erin to talk about the contributor program, and we'll have to wrap it up pretty quick here.
Yep. So we've been talking about the Continuum contributor program for the past couple sessions for sure. Again, we'd love to have people involved. Everyone here who's on the call, you're learning a whole lot about how the inner workings of Continuum work. So you guys are perfect people to be a part of Continuum contributors and help out either in software development, so actually getting into the code and making some changes on the framework, or helping out in our new R&D methods. Whether you want to investigate a new weight loss model or see is there something that we could adjust a little bit differently, a different way to optimize database. There's a bunch of different things that can happen between the software development as well as R&D portions of Continuum. So we invite everyone to be involved, be a part of Continuum, and have your little fingers all in it. So if you are interested in becoming a contributor, just go to the website, continuumwin.com/contributors, and give us a shout and let us know. And that is it for us today. So we made it just in time. So thank you so much for joining us. We had a lot to go through. So thanks for your patience, for listening through all these derivations. It probably felt like you were back in college with all these calc equations. We'll have our next town hall in about 2 months where we'll be talking about surface roughness and displacement height and those key chunks of the next portion of our continuum model. So again, thank you so much for joining us. We'll have these slides PDF'd and onto our website here shortly, as well as the recordings of these as well. And then our email addresses, again, are at the bottom, liz@onepower.com and Erin@onepower.com. So thank you again, and we will hopefully see you in 2 months.